Very warm welcome to Ethiopedia. I am Dasu Birjit. In this section we will solve linear programming problems for maximization by using graphic method. Those of you who didn't follow the first video lecture, please refer back because this session is not as detailed as the previous session. Now let's directly proceed to first question. A company produces two types of products, A and B. The volume of unit A sold is at least 75% of the total sales of both A and B. The company can't sell more than 100 units of type A. Both products use the same raw material, of which a maximum daily availability is 240 kg. The usage rates of raw material are 2 kg per unit of A and 4 kg per unit of B. The profit generated per unit of A sold is $20 and that of per unit B sold is $50. Determine the optimal product mix for the company. If we evaluate this problem against the criteria stipulated for linear programming problems, it satisfies all the requirements. Thus, this problem qualifies to be considered as linear programming problem. On the other hand, the decision variables in the problem are only two, that is type A and type B product. Hence, it's appropriate to use graphic method for solving the problem. As we discussed in linear programming problems, video lecture part 1, the under-mentioned 5-step approach is recommended for solving linear programming problem by using graphic method. Step 1. Formulate a complete mathematical model. Operations carried out in this step includes determining the objective function, identifying the decision variables and constraints, writing the objective functions and constraints in terms of decision variables, and analyzing any restrictions demanded like non-negativity restriction. What is inquired in this problem is to determine the optimal product mix. That's a proportion of type A and type B products that combinedly gives maximum profit. So the decision variables or the unknowns to be determined are type A and type B product, and the objective function is profit maximization, or the objective is profit maximization. The profit maximization function is the sum of the two products to be produced after multiplied by their respective unit profit. To write this function, let x1 is equal to type A product and x2 is equal to type B product. So the objective function is zmax is equal to 20x1 plus 50x2. 20, the coefficient of x1 is the amount of profit generated by unit type A sold, and 50, the coefficient of x2 is the amount of profit generated by type B sold. It's mentioned in the problem that the volume of unit A sold is at least 75% of the total sales of both A and B, meaning 0.75 times the sum of A and B sold, that is 0.75 times x1 plus x2, is always less than or equal to the volume of A sold, that's x1. So the constraint associated with sales volume is 0.75 times x1 plus x2 is always less than or equal to x1, or negative 0.25 x1 plus 0.75 x2 less than or equal to 0. This is the sales volume constraint. To find this constraint, simply multiply each symbol in the bracket by 0.75 and subtract x1 from 0.75 x1 to get the value negative 0.25 x1 plus 0.75 x2. Again, it's mentioned in the problem that the company can't sell more than 100 units of type A, hence x1 less than or equal to 100. This is a constraint associated with product A daily sales volume. The total raw material available is 240 kg and the consumption per unit type A and type B product is 2 kg and 4 kg respectively. Thus the constraints associated with input material is 2x1 plus 4x2 less than or equal to 240. 2. The coefficient of x1 is the consumption by unit type A, and 4. The coefficient of x2 is the consumption by unit type B, and 240 the total raw material available. The company can produce neither negative type A nor negative type B product, hence both x1 and x2 are positive, that is x1 greater than or equal to 0 and x2 greater than or equal to 0. Therefore, the complete mathematical model is zmax is equal to 20x1 plus 50x2. This is the objective function, subject to negative 0.25x1 plus 0.75x2 less than or equal to 0, sales volume constraint. x1 less than or equal to 100, this is product A daily sales volume constraint. 2x1 plus 4x2 less than or equal to 240, this is the raw material constraint. x1 greater than or equal to 0 and x2 greater than or equal to 0, this is the negativity restriction. Step 2, draw the graph of each constraint and decision variables. Put one of the decision variable on the y-axis and the other decision variable on the x-axis. Since both x1 and x2 are positive, the variable on the y-axis starts from 0 and extends upward, and similarly, the variable on the x-axis starts from 0 and extends to the right. For this particular case, let's position product type B or x2 on the y-axis and product type A or x1 on the x-axis. To draw the graph of sales volume constraint, that is negative 0.25x1 plus 0.75x2 less than or equal to 0, first substitute the inequality by equation and draw the straight line graph for negative 0.25x1 plus 0.75x2 is equal to 0. Assign any 2 points in the first quadrant that satisfies the equation negative 0.25x1 plus 0.75x2 is equal to 0. If x1 is equal to 0, then negative 0.25 times 0 plus 0.75x is equal to 0, meaning x2 is equal to 0. So 0, 0 can be the first point or the first order pair. As we discussed in the video lecture 1, positioning the 2 points at the x-intercept and y-intercept is advantageous as one of the 2 order pairs is already known, that is 0. But in this particular case, since the graph passes at 0, 0, both x-intercept and y-intercept are 0, 0, so we need to have at least one point or order pair to draw a straight line graph. To determine this point, let x1 is equal to 6, then negative 0.5 times 6 plus 0.75x2 is equal to 0, meaning x2 is equal to 2. So the second order pair can be 6, 2. This might be arbitrarily located somewhere around here. Draw a straight line by joining the 2 points. So the graph might look like this. All points satisfying the equation negative 0.25x1 plus 0.75x2 is equal to 0 lie in the solid line. Those satisfying negative 0.25x1 plus 0.75x2 less than 0 lie below the solid line. Hence the solution space or the valid side for this constraint is the region between a straight line graph and the graph of x1. The method how the feasible solution space is identified is already covered in linear programming problem video lecture part 1, so please refer it back if it's not clear for you. The region shaded with yellow color is the valid side for this constraint. To draw the graph of product A daily sales constraint, that is x1 less than or equal to 100, substitute the sign less than or equal to by the sign is equal to, and draw a vertical line starting at 100, 0 and extends upward. So the vertical line might pass somewhere around here. As usual, all points satisfying x1 is equal to 100 lie on the solid vertical line, and those points satisfying x1 less than 100 lie in the region between y-axis and x1 is equal to 100. Therefore, the valid side or the solution space that satisfying both negative 0.25x1 plus 0.75x2 less than or equal to 0 and x1 less than or equal to 100 is the region shaded with red color. All the order pair in the region shaded with red color satisfy both inequalities, that is negative 0.25x1 plus 0.75x2 less than or equal to 0 and x1 less than or equal to 100. To draw the graph of raw material constraint, that is 2x1 plus 4x2 less than or equal to 240 in the same xy plane, substitute the sign less or equal to by equality and draw the graph of 2x1 plus 4x2 is equal to 240. To compute these intercepts, simply substitute 0 in place of x2 in the equation and solve for the x-intercept because x2 is 0 at all points on the x-axis. Similarly, substitute 0 in place of x1 in the equation to determine x2 or y-intercept because x1 is 0 at all points on the y-axis. Then draw a straight line graph by joining the 2 points. So this graph might look like this. Finally, the valid side or the side feasible to all the 3 constraints is the region shaded with blue color. Step 3. Determine the valid side for each constraint line. The valid side for each constraint line and combined constraint is already determined in step 2 alongside drawing the graph. Step 4. Determine the feasible region and extreme points. The feasible region is the region where all points in the region satisfy all constraints. That's x1 less than or equal to 100, negative 0.25 x1 plus 0.75 x2 less than or equal to 0, and 2x1 plus 4x2 less than or equal to 240. The feasible region is the region where all points in the region satisfy all constraints, that is, x1 less than or equal to 100, negative 0.25 x1 plus 0.75 x2 less than or equal to 0, and 2x1 plus 4x2 less than or equal to 240. The feasible region encompasses solution points within the blue color region and those in the boundary which is in contact with the blue color region. Therefore, the feasible region is bounded at the bottom by the graph of x1, at the right by the graph of x1 is equal to 100, at the right top by the graph of 2x1 plus 4x2 is equal to 240, and at the left top by the graph of negative 0.25 x1 plus 0.75 x2 is equal to 0. Extreme points are points of intersection between decision variable with another decision variable with constraint, or one constraint with another constraint on the boundary in contact with the feasible region. Here, point O, the intersection of the 3 lines, that's product type A or x1, product type B or x2, and the daily sales volume constraint, that's negative 0.5 x1 plus 0.75 x2 is equal to 0. Point A, the intersection between daily sales volume constraint, that's negative 0.25 x1 plus 0.75 x2 is equal to 0, and the raw material constraint, 2x1 plus 4x2 is equal to 240. Point B, the intersection between raw material constraints, 2x1 plus 4x2 is equal to 240, and product A daily sales volume constraint, x1 is equal to 100. And point C, the intersection between product type A or x1 and product type A daily sales volume constraints, that's x1 is equal to 100, are extreme points. It's pretty simple to compute the order pair of these extreme points as point O is equal to 0, 0, point A is equal to 72,24, point B is equal to 100, 10, and point C is equal to 100, 0. If you face any difficulty in computing these extreme points, refer back the linear programming problem video lecture part 1 or leave me your comment for further explanation on this point. The last step, step 5, compute the optimal solution. To determine the optimal solution, take the objective function and compute its amount at the 4 extreme points. So the objective function is zmax is equal to 20x1 plus 50x2. Thus zmax at point A is equal to 20 times 72 plus 50 times 24 is equal to $1,640. Zmax at point B is equal to 20 times 100 plus 50 times 10, which is equal to $1,500. Zmax at point C is equal to 20 times 100 plus 50 times 0, which is equal to 2000. Zmax at point O is equal to 20 times 0 plus 50 times 0, which is equal to 0. The maximum profit of 2,640 is fetched at point or at the product mix of 72 units of type A and 24 units of type B. Therefore, the optimal solution is 72 units of product type A and 24 units of product type B. Question number 2. A company wishes to invest $30,000 over the next year in 2 types of investments, investment A and investment B. investment A yields 8% and investment B yields 10%. Data from market research recommends an allocation of fund of at least 25% in A and at most 50% in B. How the fund should be allocated to the two investments. For this and the upcoming two questions, we will not go to minute detail like question 1, because once you grasp the basic principles, it's not difficult to solve such problems. In this question, we inquire for a portion of fund between investment A and investment B. So the decision variables are fund for investment A and fund for investment B. Fund apportion is subjected to fund limitation and limitation imposed by market research recommendation of fund allocation. So the constraints are fund limitation and fund allocation. Funds should be allocated in a manner that can maximize yield from the investments. Thus the objective function is yield maximization. With these givens, let's proceed to the 5 steps for solving the problem. Step 1. Formulate complete mathematical model. Let x1 is equal to fund for investment A and x2 is equal to fund for investment B. Objective function, which is yield maximization, is the sum of yield from the two investments after they are multiplied by yield percentage is Zmax is equal to 0.08 x1 plus 0.1 x2, subject to fund allocation constraint x1 greater than or equal to 9,000. Here 9,000 is 25% of the available total fund of 36,000, and x2 less than or equal to 18,000. Again 18,000 is 50% of the available total fund. Fund limitation constraint x1 plus x2 less than or equal to 36,000. Non-negativity restriction x1 greater than or equal to 0 and x2 greater than or equal to 0. Step 2. Draw the graph of decision variables and constraints. As usual, decision variable position on the y-axis starts from 0 and extend upward, and that on the x-axis starts from 0 and extends to the right. Draw the graph of the equation of each constraint, that is, x1 is equal to 9,000, x2 is equal to 18,000, x1 plus x2 is equal to 36,000. It's simple to draw the graph of this constraint as x1 is equal to 9,000 is a vertical line starting from 9,000, 0 at the x-axis and extends upward. x2 is equal to 18,000 is a horizontal line, starts from 0, 18,000 at the y-axis and extends to the right. And the graph of x1 plus x2 is equal to 36,000 is a downward sloping graph with x-intercept 36,000, 0 and y-intercept 0, 36,000. Step 3. Determine the valid side of each constraint. All values computed to x1 is equal to 9,000, x2 is equal to 18,000, and x1 plus x2 is equal to 36,000 are located on the respective solid lines. On the other hand, x1 greater than 9,000 includes all points to the right of the vertical line x1 is equal to 9,000. x2 less than 18,000 includes all points below the horizontal line x1 is equal to 18,000. And all points satisfying x1 plus x2 less than 36,000 are located below the slant line x1 plus x2 is equal to 36,000. Thus, the region shaded with blue color is the valid side for all the 3 constraints. Step 4. Determine the feasible region and extreme points. The region shaded with blue color is a feasible region. Points of intersection of one constraint with another constraint and constraint with decision variable which are in contact with the shaded region are extreme points. In this graph, points we assigned as W, X, Y, and Z are extreme points. The order pair for these points can simply be assigned as W is equal to 9,000, 0, X is equal to 9,000, 18,000, Y is equal to 80,000, 18,000, Z is equal to 36,000, 0. To determine this order pair, just take equations of the lines that intersect to form this point and solve them simultaneously. The last step, step 5, compute the fund allocation. Take the objective function and calculate the yield at each extreme point. The objective function is Zmax is equal to 0.08 x1 plus 0.1 x2. Zmax at point W is equal to 0.08 times 9,000 plus 0.1 times 0, which is equal to $720. Zmax at point X is equal to 0.08 times 9,000 plus 0.1 times 18,000, which is equal to $2,520. Zmax at Y is equal to 0.08 times 18,000 plus 0.1 times 18,000, which is equal to $3,240. Zmax at Z is equal to 0.08 times 36,000 plus 0.1 times 0, which is equal to $2,880. The maximum yield of 3,240 is achieved when the company allocates $18,000 for each in investment A and investment B. Thus, the fund should be allocated $18,000 in investment A and $18,000 in investment B. Question number 3. ChemLab uses raw material 1 and 2 to produce 2 domestic cleaning solutions, A and B. The daily availabilities of raw material 1 and 2 are 1,500 and 1,350 units respectively. 1 unit of solution A consumes 5 units of raw material 1 and 6 units of raw material 2, and 1 unit of solution B uses 5 units of raw material 1 and 4 units of raw material 2. The profit per unit of solution A and B are $6 and $7 respectively. The daily demand for solution A lies between 30 and 150 units, and that of solution B lies between 40 and 200 units. Find the optimal production amounts of A and B. This is the first question. Second question, how much is the slack associated with the raw materials? We can understand from the question that the goal of the company is to maximize profit by a portion of the daily amount of cleaning solution A and B to be produced. Hence, profit maximization is the objective of the company, and cleaning solution A and B are decision variables. The profit maximization function is limited by the availability of raw material 1 and 2 and daily sales volume of cleaning solution A and cleaning solution B. Thus, the constraints are type 1 and type 2 raw materials and each solution daily sales volume. For ease of formulating mathematical model, let's tabulate the givens in the form like this. Having this information, let's go to solving the problem by following the steps. Step 1. Formulate complete mathematical model. Let x1 is equal to cleaning solution A and x2 is equal to cleaning solution B. Objective function, which is profit maximization, is the sum of profit generated from sales of 2 cleaning solutions after they are multiplied by their unit profit is Zmax is equal to 6x1 plus 7x2, which is subject to type 1 raw material constraint, 5x1 plus 5x2 less than or equal to 1,500. Type 2 raw material constraint, 6x1 plus 4x2 less than or equal to 1,350. Type A daily sales volume, 30 less than or equal to x1 less than or equal to 150. And type B sales volume, 40 less than or equal to x2 less than or equal to 200. And non-negativity restrictions, x1 greater than or equal to 0 and x2 greater than or equal to 0. Step 2. Draw the graph of the decision variable and constraint. As usual, decision variables position on the y-axis start from 0 and stretch upward, and that on the x-axis start from 0 and stretch to the right because both decision variables are positive. Then, draw the graphs of equations of each constraint, that is 5x1 plus 5x2 is equal to 1,500, 6x1 plus 4x2 is equal to 1,350, x1 is equal to 30, x1 is equal to 150, x2 is equal to 40, and x2 is equal to 200. 5x1 plus 5x2 is equal to 1,500 is a negative slope slant line starting from 0, 300 at the y-axis and end up at 300, 0 at the x-axis. 6x1 plus 4x2 is equal to 1,350 is also a negative slope slant line starting from 0, 337.5 at the y-axis and end up at 225, at the x-axis. x1 is equal to 30 and x1 is equal to 150 are vertical lines starting from 30, 0 and 150, 0 and extends upward respectively. x2 is equal to 40 and x2 is equal to 200 are horizontal lines starting from 0, 40 and 0, 200 and extend to the right respectively. Step 3. Determine the value side of each constraint. All values computed to 5x1 plus 5x2 is equal to 1500. 6x1 plus 4x2 is equal to 1350. x1 is equal to 30. x1 is equal to 150. x1 is equal to x2 is equal to 40, and x2 is equal to 200 are located on the respective solid lines. On the other hand, 5x1 plus 5x2 less than 1500 include all points between the line and the origin. 6x1 plus 4x2 less than 1350 also include all points between this line and the origin. 30 less than x1 less than 150 include all points between the vertical lines x1 is equal to 30 and x1 is equal to 150, and all points satisfying 40 less than x2 less than 200 are located between horizontal lines x1 is equal to 40 and x1 is equal to 200. Thus, the region shaded with yellow color is a valid side for all the three constraints. Step 4. Determine the feasible region and extreme points. The region shaded with yellow color is a feasible region. Points of intersection of one constraint with another constraint which are in contact with the shaded region are extreme points. In this graph, points we assigned as P, Q, R, S, and T are extreme points. The order pair for these points can simply be solved as P is equal to 30, 40, Q is equal to 30, 200, R is equal to 91.67, 200, S is equal to 150, 112.5, and T is equal to 150, 40. To determine these order pairs, just take equations of lines that intersect to form the respective points and solve them simultaneously. The last step, step 5, compute the cleaning solutions A and B. Take the objective function and calculate the profit at each extreme point. The objective function is zmax is equal to 6x1 plus 7x2. Zmax at point P is equal to 6 times 30 plus 7 times 40, which is equal to $460. Zmax at point Q is equal to 6 times 30 plus 7 times 200, which is equal to $1,580. Zmax at R is equal to 91.67 times 6 plus 7 times 200 is equal to $1,950. Zmax at S is equal to 6 times 150 plus 7 times 112.5, which is equal to $1,687.5. Zmax at T, 6 times 150 plus 7 times 40, which is equal to $1,180. Maximum profit of $1,950 is achieved when the chem lab produce 91.67 unit of cleaning solution A and 200 unit of cleaning solution B. Thus, the optimal product mix is 91.67 unit of cleaning solution A and 200 unit of cleaning solution B. The second question, which is the slack associated with the raw materials. As we know, slack is the amount of input material left unused. To determine the amount left unused, we have to calculate the total consumption because amount unused is the difference between amount available and amount used. Amount to be produced is already determined as 91.67 unit of cleaning solution A and 200 unit of cleaning solution B. The consumption of each raw material for producing the mentioned quantity of product is raw material type 1 consumption, which is equal to 5x1 plus 5x2, which is equal to 5 times 91.67 plus 5 times 200, which is equal to 1458.35 unit. Raw material type 2 consumption, 6x1 plus 4x2, which is equal to 6 times 91.67 plus 4 times 200. This is equal to 1350 unit. Therefore, the slack associated from each raw material can be tabulated in the form raw material type, raw material 1 and raw material 2, amount available, which is already given, raw material type 1 given 1500, raw material 2 given 1350, amount used, which is calculated, raw material 1 used 1458.35, raw material 2 used 1350, slack, which is the difference between amount available and amount used, raw material type 1 slack, which is equal to 1500 minus 1458.35, which is equal to 41.65, raw material type 2 slack, 1350 minus 1350, which is equal to 0. Yared, who is a freshman student at St. Mary's University, wants to apportion his 11 hours a day between work and play in order to maximize his pleasure for both work and play. He estimates that play is twice as much fun as work. He also wants to study at least as much as he plays. However, Yared realizes that if he is going to get all his assignments done, he can't play more than 4 hours a day. How should Yared allocate his time to maximize his pleasure for both work and play? From this question, we can clearly discern that the objective is maximizing pleasure. The decision variables are play hours and work hours, and constraints are limited total hours of a day, limited working hour, and a portion of hours between playing and working. With these informations in mind, let's move on to solve the problem by following the steps. Step 1, formulate the complete mathematical model. Let x1 is equal to working hours and x2 is equal to playing hours. Objective function, which is pleasure maximization, is the sum of pleasure gained from work and play after they are multiplied by their unit of fun they can produce, is z max is equal to x1 plus x2, which is subject to limited hours of a day, which is x1 plus x2 less than or equal to 11. A day playing hour limitation, which is x2 less than or equal to 4. Relationship between work hour and play hour, x1 greater than or equal to x2, and non-negativity restrictions, x1 greater or equal to 0 and x2 greater or equal to 0. Step 2, draw the graph of decision variable and constraint. As usual, the decision variable position on the y-axis and x-axis starts from the origin and stretches to upward and to the right respectively, because both decision variables are greater than or equal to 0. Then draw the graph of equation for each constraint, that's x1 plus x2 is equal to 11, x2 is equal to 4, x1 is equal to x2. x1 plus x2 is equal to 11 is a downward sloping slant line starting from 0,11 on the y-axis and end up at 11,0 on the x-axis. x2 is equal to 4 is a horizontal line starting at 0,4 and stretched to the right. x1 is equal to x2 is a positive slope graph starting from the origin or 0,0 and extend away from the origin. Step 3, determine the valid side of each constraint. All values computed to x1 plus x2 is equal to 11, x2 is equal to 4, and x1 is equal to x2 are located on the respective solid lines. On the other hand, x1 plus x2 less than 11 includes all points between the line and the origin. x2 less than 4 includes all points between the line and the graph of x1, that's the horizontal axis, and all points satisfying x1 greater than x2 are located between the line x1 is equal to x2 and the horizontal axis. Thus, the region shaded with red color is the valid side for all the three constraints. Step 4, determine the feasible region and extreme points. The region shaded with red color is the feasible region. Points of intersection of one constraint with another constraint and constraint with decision variable which are in contact with the shaded region are extreme points. In this graph, points we assigned as E, F, G and H are extreme points. The order pair for these points can be determined by simultaneously solving the lines that intersect to form that particular point as E is equal to 0,0, F is equal to 4,4, G is equal to 7,4 and H is equal to 11,0. Step 5, complete the hour allocation. Take the objective function and calculate the pleasure at each extreme point. The objective function is z max is equal to x1 plus 2x2. Z max at point E is equal to 1 times 0 plus 2 times 0, which is equal to 0. Z max at F is equal to 1 times 4 plus 2 times 4, which is equal to 12. Z max at G is equal to 1 times 7 plus 2 times 4, which is equal to 15. Z max at H is equal to 1 times 11 plus 2 times 0, which is equal to 11. Maximum pleasure of 15 achieved when Yared allotted his time as 7 hours for work and 4 hours for play. Therefore, the day 11-hour allocation between work and play should be 7 hours for work and 4 hours for play. That's for all today. Next time we will see linear programming problem for minimization. I wish you all the best in every single minute of your life. Goodbye.